Guys, it's Mrs. Duskevich. I just want to go over with you another periodic trend of the ionic radius. So first off, with the ionic radius, we have to look at cations and anions. Cations are always smaller than the original atom, and the entire outer principal energy level is removed during ionization. So I want to draw a couple little pictures here for you just to help you out. So the entire outer principal energy level. So let's take, for example, calcium. Let's pretend we're working with calcium, and if we write calcium's electron configuration, we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So therefore, if calcium loses its two outermost electrons, we're going to basically take out our whole entire energy level, which is 4. So that's what that means. The entire outer principal energy level is removed. So let's think about this here. Calcium has 20 protons in its nucleus, and it has 20 electrons in its electron cloud. Where if we make calcium's cation, which is 2 plus, we still have 20 protons in the nucleus, but instead we have 18 electrons in the electron cloud. So now we have to think about these 20 protons are pulling on these 20 electrons, but look here, we have 20 protons pulling on 18 electrons. So therefore, that's going to have a stronger pull. Hence, the cation is smaller. Notice cations are always smaller. Let's think about this in terms of, here's just a picture with a Bohr model. So this particular picture indicates sodium. So we have a sodium atom with one valence electron. Notice our valence electron's right here. Okay, so that valence electron. And the valence electron's lost in the ion formation. So the valence electron goes away, and therefore we lose the entire outer shell or the entire principal energy level. When we have this entire principal energy level gone, the effective nuclear charge on the remaining electrons increase, meaning now we have 11 protons here and only 10 electrons total. So therefore our effective nuclear charge is increasing. Those remaining electrons then are pulled in closer to the nucleus, and so the ionic size decreases. Result, we get a smaller sodium cation compared to the sodium atom itself. Now, in an ionic radius, conversely, anions are always larger than the original atom. These electrons are added to the outer principal energy level. Let's take chlorine, for example. Chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so if we have chlorine minus, we're going to have 1s2, 2s2, 2p6, 3s2, now a 3p6. So let's think about this. We're adding them to the outer principal energy level. So instead of losing that entire principal energy level, we're actually filling it. So let's look at chlorine. We have initially 17 protons, and we have 17 electrons. So we do have a relatively strong effective nuclear charge here, but then we have 17 protons and 18 electrons when we have a chlorine anion. So therefore, those 18 electrons, there's less of a nuclear charge because the 17 can't pull the 18 electrons like it can the 17 electrons. So therefore, the anion is going to be larger than the neutral atom. Here's a little anion formation. So here's chlorine in itself, has 7 valence electrons this time. One electron's added to the outer shell. Now it has 8 valence electrons. The effective nuclear charge is reduced and the electron cloud expands. Now, we still have 17 protons, so the number of protons isn't reduced, but that effective nuclear charge is reduced because now there's 18 electrons to hold in. So therefore, the electron cloud will expand. So just remember, between the two here, we have, with cations and anions, you want to basically be able to determine and look at its regular neutral atom with its cation or the neutral atom with its anion. The best thing to do is look at these effective nuclear charges. There's one more thing I do want to show you, and I'm just going to show you up here in this little space, is I do want to show you, for example, what if we have something like a calcium 2 plus and a potassium 1 plus? And so then we have to look at those cations and say, okay, which one's going to be bigger? So the calcium 2 plus has 20 protons and it has 18 electrons. A potassium 1 plus has 19 protons and 18 electrons. So therefore, think about this. This 20 protons is trying to hang on to these 18 electrons, where 19 protons is trying to hang on to 18 electrons. These 20 protons are going to be able to hold them tighter, meaning it has a higher effective nuclear charge. So even though there's the same number of electrons in both, we have a higher effective nuclear charge for the calcium cation compared to the potassium cation. I think the best way to do this is really think about and maybe draw a little picture like I have been of the number of protons with the electrons and then reason it based on its effective nuclear charge. You guys got this.